G'day everybody. Today's lesson we're looking at Newton's method. We'll talk about what does Newton's method do, how does it work. We'll see that there is an iterative formula for this method. We'll have a look at what might an example look like when we're using Newton's method. And we'll finish the lesson by talking about some of the reasons that Newton's method will sometimes fail. So Newton's method is an algorithm for finding solutions to f of x equals 0. It's very different to algebraic approaches to that task. It looks very different, but doesn't matter really what type of function it is. If we can graph that function, we can probably use Newton's method to find the root of that function, to find the solution. It's a graphical approach. We'll see how we use tangents when we are using Newton's method. It's an approach that makes use of the derivative, so it's an application of calculus. Instead of just using f of x, we do use f of x, but we're also going to use the derivative f prime of x. And the process is not algebraic. It's what you might say is a numerical approach or an iterative approach. So this is what Newton's method basically looks like. If we're solving f of x equals 0, we imagine that there's a graph for f of x, so it might look like this simple curve here. And if we're looking for the solution to f of x equals 0, in terms of the graph, that means we're trying to find the root, another word for the x-intercept. Newton's method starts with a pure guess, so we guess what the root might be. And then a tangent is used to find a closer estimate, and this is how we do that. We take the value of x that we have guessed, and we draw a tangent from the curve, and that tangent goes down and intersects the x-axis. So there's our guess, there's the point at which we're making a tangent, and that straight line tangent comes down and intersects the x-axis. So in this case, our x-intercept has got closer to the actual root that we're finding. This was our guess, and this actually becomes our estimate, or our next guess, if you like. And then we repeat the process. So using that next value of x, x1, we draw a tangent from the curve f of x, and then we look at where that second tangent intersects the x-axis. And that becomes our next estimate. And again, we use that next value of x, x2, we think about a tangent, and that gives us our next estimate. And so you can see that from one process to the next, we've got values of x that are getting closer and closer to the root that we're actually finding. We'll never actually pass that root, so it's only going to get closer and closer. So in other words, our estimate is improving. Typically, we never actually reach the zero of the curve. We're just going to get closer and closer. Theoretically, there will always be some distance between the actual root and our estimate, but at some point, we'll be close enough. We'll be satisfied that our estimate is precise enough, and we can stop. So you can see how this approach is basically a few steps that are being repeated over and over. So we started with a guess. That was basically an estimate of the root, if you like. We used that to form a tangent, and the x-intercept of that tangent was found, and that becomes the estimate of the root. And then we draw another tangent, that gives us another x-intercept, and so we've got another estimate. And this just keeps going and going until we have found a root, or until we are close enough to root to know basically what it is. So let's have a look at this in terms of the function and the derivative and what's going on mathematically. So here you can see our guess, and there's our tangent, and that tangent has an x-intercept. So x0 is the guess, In this case, I'm going to refer to that as the previous estimate. And that tangent has a gradient that is given to us by the derivative. So at this point, that tangent has a gradient that is f prime of x when x is equal to x naught. And the tangent intersects the curve at this point, x naught, and there's f of x naught. So the gradient is f prime of x naught, and the y value is f of x naught. We've got the derivative and we've got the function. So we can basically use the equation of a straight line. And so here's my mx minus x1, and here's our y1 over here. So we've got our gradient, our x minus x naught, plus f of x naught. And if we are looking for x naught, what we're saying is that y is equal to 0. So when we substitute x1 and y equals 0, this is our equation, and we want to solve that equation for x1. And so basically rearranging and solving for x1 gives us this equation here. And so in one go, in one calculation, we can find our next estimate. So this is how we calculated the first estimate. In a similar way, this will be how we calculate the second estimate. So the first time we started with x naught and we got x1. The second time we used x1 and we got x2. And then we've got our third estimate, and so on. So in general, the same thing is happening. If I call my previous estimate xn, and I call my next estimate xn plus 1, then this is the expression that will give us that nx plus 1. And that's the formula for Newton's method. So once we've got this formula, we don't really have to worry too much about the graph and the diagram anymore. So in this formula, just to spell it out, our previous estimate we're referring to as xn. We're going to use the function of that value, f of xn, and we're going to use f prime of xn as the derivative, and that will give us the next estimate. So the next estimate is the previous estimate minus f of xn divided by f prime of xn. The only other thing we have to consider is what is going to be our initial guess. What are we starting with? And in many cases it can be anything, but later in the lesson we'll see how sometimes Newton's method will fail based on what we start with. Let's have a look at an application of Newton's method. In this case, we're going to use the method to find an approximation for the square root of 5. And you can see the function that we're going to work with is f of x equals x squared minus 5. So if we're looking for when f of x equals 0, a solution to that equation is the square root of 5. So we know that the square root of 5 is actually the root. When we use Newton's method, we're not going to get a square root, we're going to get a decimal value. So in this case, we're going to use the root that we solve with Newton's method to give us a good approximation for the square root of 5. And so here we're going to get set up for using Newton's method. There's my function, f of x, x squared minus 5. The derivative of that is 2x, so f prime of x equals 2x. And so here is Newton's method. X of n plus 1 will be x of n minus f of xn. So here you can see I'm using the function with my previous guess and the derivative with my previous guess. I'm just pulling this out of the air. We're going to use an initial guess of 10. And 10 is in no way close to the square root of 5. So it's really quite a long way away. So when we find our next estimate, I'm going to say that x1 will be 10 minus f of 10, 10 squared minus 5, divided by the derivative when x equals 10, which is 2 times 10. and that has given me a value of 5.25. So already I've gone from 10 to 5.25 when trying to find an approximation for the square root of 5. I'm going to use the CAS calculator here. You can see how I've done that with the CAS calculator. I'm just using the rule that I found here for using Newton's method, and I'm substituting x equals 10. There's my first guess. There's my next estimate. So I've now gone to 3.10119, etc. And you can see here I've just copied and pasted the previous answer and substituted it into exactly the same expression. And again, I've copied the previous answer, substituted into the same expression. So this is iteration, this is just repetitive. And you can see how my estimate is changing. At the start it changed by quite a lot, but now it's not changing by so much. Let's jump forward a few. We get x4, x5, x6. So now you can see even by the time I get to the sixth estimate to 4 decimal places, or even rounding off to 5 decimal places, those two guesses are pretty much the same. And when we look at our next guess to 10 decimal places, it hasn't changed at all. And so comparing our seventh estimate with the actual square root of 5 when we find an approximation using the calculator to 10 decimal places, it's exactly the same value. So we've used Newton's method to solve x squared minus 5 equals 0, and in turn that has given us an approximation for the square root of 5. I mentioned that sometimes Newton's method will fail, so we're going to look very quickly at just a few reasons why this might happen. So in this diagram here, you can see that we're looking for the root here, and there's our first, or our guess, and then using our tangents we've gone over to this side, and then using a tangent down here, our next x-intercept is over here, and then our third one is over here. And so we're actually gradually getting further and further away from the solution that we're trying to find. It's not converging towards the solution, it's diverging. In this case, we've got it could be a polynomial, a cubic equation, for example. We actually want to find this solution, but because our guess is too far away, we've ended up finding a solution is a solution to the polynomial, but it's not the one that we're actually trying to find. So we could just change our initial guess and hopefully find another solution that we're looking for. In this third example, it's another example of how it's not diverging, but it's going backwards and forwards. So our first guess is here, our second guess is here, and then we go back to here, and then back to here, and we just go backwards and forwards over and over again without ever getting closer and closer to the desired solution, to the root. So a guess somewhere closer to the desired solution would be better off. And the last example we'll talk about could be a freak occurrence where our guess ends up being the value of x at a stationary point. And the problem there is with the tangent is parallel to the x-axis, and so we're not going to find our next estimate because the tangent should be intersecting the x-axis. So again, if that case happens, we just change our initial guess, and then we should converge towards at least one solution to that equation. So that's Newton's method. We've talked about what it is and how it works. The important part of the lesson is we've seen the iterative formula for this method. You should write that down. That's the one you will use over and over again for these problems. We've seen an actual application of it. In this case, we used it to approximate the square root of 5. And we've had a brief discussion about why Newton's method sometimes fails. Please write down any questions that you have and complete the Google form to log in your attendance, check your understanding. Thanks very much.